Okay, so the whole point of doing this electron configuration thing and the orbital rotation is to talk about the periodic trends, why certain things do certain things. So for example, one of the things we talked about with electron configuration was common charge. Okay, so that's one of the things we're going to talk about. Periodic trends are patterns that are observed in elements and are repeated on the periodic table. For example, one of the ones is I told you guys, put at the top of fluorine, put a -1. And that means everything in that column gets a -1 charge. That is a periodic trend. So valence electrons are it, ionic charge, that would be this thing, atomic radius, ionization energy. Those are all four periodic trends we're going to talk about. So valence electrons we'll talk about first. They are the electrons in the highest principal energy level. That would be the number in front of S and P. Okay, whatever that is, the electrons that live there. Okay, so if you were to write the electron configuration for carbon, 1s2, 2s2, 2p2. Silicon is 1s2, 2s2, 2p6, 3s2, 3p2. GE is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. And I'm going to do the short way for tin. Krypton, 5s2, 4d10, 5p2. So if you look at all of those, they're all in the same family. If I'm looking for the electrons that live in the highest number S and P's, I'm looking right here. The electrons that live there are 2 plus 2, 4. And if I'm looking for silicon, the highest level S and P's, I have, again, 2 plus 2 equals 4. If I look at GE, now GE is a little tricky because my 4s is here and my 4p is there, separated by the 3d. But I'm just looking at the highest number S and P orbitals, this guy and this guy. So it is still 2 plus 2 equals 4. And then the last one, again, even if I do it the short way, I still get my highest number S and P's written out. S and P's, 2 plus 2 equals 4. And all four of those elements have 4 valence electrons. That's the number of valence electrons each one's have. That's why they're in the same column on the periodic table. All elements in the same family of the periodic table have the same number of valence electrons. This would be columns. Okay? And elements in the same family have similar chemical properties because of those valence electrons. And literally, you can count across on your periodic table and figure out how many they have, but this is where it comes from, is their electron configuration. That was the whole point of learning it. So the number of valence electrons something has. Column 1 has 1. Column 2 has 2. Column 13 has 3. So this would be where boron is. Carbon is here, right? We already discovered that one has 4. Nitrogen, everything in that column has 5. Oxygen, everything has 6. Fluorine, everything has 7. And under neon, everything has 8. Helium doesn't count. Helium actually only has 2 because it only has 2 electrons. These guys, you can't make that determination for. Okay, you actually do have to write out the electron configuration for these guys. But the other ones are simple. All you have to do is look at what column they're in and count. Alright, so ionic charge is tough. We talked a little bit about this before when we were doing the homework with electron configuration. Metals lose their valence electrons. Okay, so we just said how many valence electrons things have. And they lose them to form positive ions. Remember, these are the S and the P with the highest numbers in front. They lose them all, and it forms positive ions. Nonmetals fill up. They gain valence electrons to completely fill up their S and their P's. Instead of emptying them, they fill them. And so if I was to write the electron configuration, the common charge for Ca, it is argon, 4s2, and it is a metal. And since it is a metal, I'm going to look at it losing all of its S's and all of its P's with the highest number in front. Well, the highest number in front is 4. So it's going to lose these 2 electrons and get a positive 2 charge, okay, because it's a metal. Phosphorus, on the other hand, is neon, 3s2, 3p3, but it is a nonmetal, and nonmetals gain electrons to completely fill their S and their P's. Well, the S is filled. The P is almost filled. It needs 3 more. So it's going to get a -3 charge. And so it all depends on the electron configuration. That's why I said that was so very important. Now carbon's a little tricky. Carbon is 1s2, 2s2, 2p2. Technically it's a nonmetal. And therefore it needs to fill up its S and its P with the highest coefficient. S is filled, P needs 4 more electrons, so -4 charge. But if you look at lead, which is in the same family, lead is xenon, 54, 6s2, 4f14, 5d10, 6p2. Again, S and P's, but it's a metal. It's going to lose them. Here's its S, and here's its P's. It's going to lose 4 electrons, +4. So if you remember at the beginning of the year, I told you guys to write 4 plus and minus at the top of the carbon family column. And that's because nonmetals get a -4 charge. Metals like lead and tin get a +4 charge. So that's where these charges come from. It's based on their electron configuration and their valence electrons. Atomic radius is literally the size of the atom, okay? The outside edge, the farthest out we can go. We can't go all the way to the edge because we don't know exactly where that is, but the atomic radius depends on the number of protons in the nucleus, because remember, they're positively charged, and they have an attractive force for the negatively charged electrons, and so they're going to pull them in. But according to Bohr's model, they can't pull them all the way in, and so the radius depends not only on the number of protons, but also how many circles there are between the center and the outside electron. Okay, so it depends on the protons in the nucleus and on the energy levels. So the way it works, if you wrote the electron configurations for these guys, magnesium is neon, 3s2. Barium is xenon, 5, 6s2. And if I had to compare the radius for those guys, okay, there's a big difference. Calcium is argon, 4s2. Sorry, I didn't mean to write that so small. And this is argon, 4s2, 3d10, 4p5. So now we're going to compare the radius for these guys. Which element in each group would you expect to have a larger radius and why? So in this first group, I would pick barium. And barium, because it's got 1, 2, 3, 4, 5, 6 electrons, energy levels with electrons in them. Magnesium, on the other hand, is 1, 2, 3. And it's outside electrons in energy level 3. So here, when you're comparing things in the same column, you want to compare their energy levels. Okay? Magnesium's in the 3rd row, barium's in the 6th row. Obviously, barium's going to be much bigger. So I'm going to erase that ink. And we'll talk about the next one. Okay, the next one is actually kind of counterintuitive. In this one, calcium is actually bigger. And the reason why, if you notice, they both are energy level 4. So they're both 1, 2, 3, 4. That's calcium. And bromine is 1, 2, 3, 4. So they both have their electrons 4 energy levels out. So you can't really compare energy levels with these guys. They're in the same row. That's why they're both in the 4th row on the periodic table. But what happens is this has 20 protons and this one has 35 protons. Those 20 protons are pulling on this electron, pulling it in a little bit. But this one, with there's 35 of them pulling on that electron, they pull it in much closer. So this one has a smaller atomic radius because of the protons. Okay? Oops, let me erase the ink on the slide. Alright, so atomic radius increases from top to bottom within a family. That would be these guys. Barium is bigger. And it decreases from left to right across the periodic table going within a row. And that would be these guys. Calcium's actually bigger. So here's how it works. The atomic radius decreases going this way. The atomic radius increases going down. And you can see that here. You can see the energy levels, things like that. Okay, so the largest atomic radius is right there. The smallest is here. So which atom in each group would you expect to have the largest radius? So CS, AU, and RN. CS is farthest to the left. N, AS, and BR. Okay, so AS and BR are below nitrogen, but AS is to the left. Manganese, TC, and RE. Gosh, I don't even know where they are on the periodic table, but I think RE is farther down at the bottom. Na, RB, and AR. Definitely RB. Okay, so biggest are at the bottom left, and the smallest at the top right. Okay, ionization energy is the last of our trends that we're going to talk about. And this one's kind of a weird one. The idea is it's the energy needed to take an electron, so a valence electron, and literally pop it off the atom. Now keep in mind, it's being held there because that proton wants to keep it there. So you have to add energy. It's very endothermic to pull these electrons off. So generally, increased ionization energy is related to, first of all, a small radius, because the closer it is to the nucleus, there's this thing called Coulomb's law. The closer they are, the stronger the attractive force. So if it has a small radius, the valence electron requires more energy to remove, so ionization energy increases. And if it has a stable electron configuration, so your noble gases, remember what I said about how they have completely filled energy levels and they're very stable? They are very stable, and they have the highest ionization energies of all the elements in general. And so, and like I said, stable electron configurations happen when the orbitals or the energy levels are completely filled. That makes them more stable, and its ionization, ionization energy increases if they have energy levels that are filled or orbitals that are filled. And so which group of elements will have the highest ionization energies? That would definitely be the noble gases. Alright, so electron configurations. This is 1s2, 2s1, 1s2, 2s2, 2p6, 1s2, 2s1, and this is xenon, 54, and then 6s1. So if I'm comparing just these two, 1, 2, there's my outside electron. That's for lithium. For neon, 1, 2, there's my outside electron. So in terms of the size of the atom, you know, basically right now, they look like they're about the same. They both have 2 energy levels. The big difference is this has 10 protons, this has 3 protons, so it actually pulls the atom, the atomic radius is smaller. Therefore, the ionization energy is larger. You could also say, look at that, man, it's completely filled, man, happy, happy. It's a noble gas, and that would also be true. But it's really because the atomic radius is smaller and the ionization energy is bigger, because those 10 protons are pulling on that electron much stronger than they are in lithium. Alright, so if I was to do this one, 1s2, 2s1, xenon, 6s1. So 1, 2, 1, 2, 3, 4, 5, 6. So there's my outside electron. Here's my outside electron. Again, atomic radius is smaller. Ionization energy is going to be larger. You could also look at it as the fact that this has 3 protons. This has 55 protons. Okay, but the fact that this one is such a large molecule or atom, those 55 protons really don't have much of an effect. There's this thing called the shielding effect, which would affect their ability to attract those electrons. So the more easily removed valence electron would be in lithium between these two, and in cesium between these two, because that electron is so far away. The radius is so much bigger. Ionization energy generally increases left to right across the periodic table and decreases top to bottom. So calcium, zinc, and bromine, that one's going to be higher. So it's highest, i.e. top right. Calcium, barium, beryllium, Be. N, As, and Fe, probably nitrogen. Closer to the top makes a bigger difference. Xenon, tin, and argon. Argon for sure. Okay, so the closer they are to the top right, and top makes a bigger difference than right makes a difference. So a quick summary, valence electrons are the same for all the elements in the family. Metals lose their S and P electrons to get a positive charge. Nonmetals fill up the S and P to get a negative charge. Ionization energy is greatest at the top right, least at the bottom left. Atomic radius is greatest at the bottom left and least at top right. They are definitely inversely proportional.